given f c to d in C, we say f is an S homomorphism. So we have a supply S if for all of these mu things in my prop we have a nice square commuting. So what can we do? Well, the supply gives us this map on C from C to M to M. It also gives us a map on D, so D to the M to D to the N, what supplies of D of mu. And we can go fiberwise and we can apply F sort of on each factor. So this thing should commute. So just one more statement. If every morphism F in C is a supply, is an S hom, we say S is a homomorphic supply. Okay. So how do you make sense of this sort of picture? Well, if we take this sort of comonoid example that we were talking about, where we have sort of a multiplication on C, we can copy things in C, and we can copy things in D. And this square here says that if we have some F going from C to D, there are two things we can do. We can first do the copying on C and then apply however many appropriate copies of F and get out two elements of D. Or we can apply the F first and then do the copying. And we want that to be, these things to be equal. So it's the same if we go around this way or that way. Okay. So it's taken some work to say these things abstractly, but ultimately the intuition comes back to the example that I started with. But it turns out this language is fairly powerful, so let me give a bunch of examples. So, examples. So a simple, sort of hopefully instructive example is that everything homomorphically supplies bijections. And in fact, it does so in a unique way. But what is the intuition here? Well, so it says, the definition says that for every object C, I need one of these functors that sort of instantiates bijections in C. So this means for every morphism, and the first condition says that this functor must sort of send the object M to C to the M, where C is the object I picked. So for example, if I pick some bijection like this, then S sub C of this has to be a map from C to the 3 to C to the 3. So it has to take 3 copies of C and return, and sort of be a map from 3 copies of C to 3 copies of C. And we can define a map using the symmetric monoidal structure in C. So there's the permutation and there's the identity. And so this picture looks a lot like this picture, which is partly the point. But what's sort of different is that this is really now a picture of, another way to do this is sort of think of this as if I call the grading sigma, and call that box the identity, then this is really a picture of these actual morphisms in C. And that's just the tensor product of the braiding with the identity. And then, what does the functoriality say? What do these conditions C say, for example? Well, and I'll draw the picture quickly. So this is S sub C of this morphism, which we'll call mu, as a shorthand, tensor the dth version of this. So S sub D of mu. Okay. But then there's also S sub C tensor D of mu. Now what does that look like? Well, it should look like we get two copies, so CD, 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 CD. So they're the two sort of horizontal arrows in this diagram. And the vertical arrows just say permute them to make the types work out. So the final type we want is this sort of CD, CD, CD type, which is the sort of tensor product of 3 copies of C tensor D. And so the permutations on the top end go something, I guess they're basically the example I drew over there. So blah, 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 blah. And on this end, the sort of inverse of that. So it goes C, 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 D, 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 and we commute blah, 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 blah. So the point is that these two morphisms are equal as morphisms in C. And by the magic of string diagrams, which is kind of hiding the work here, it's easy to check if I've drawn them correctly. If I haven't, then it's not easy to check. And then what does this homomorphic condition say? So this condition here, well, it says that if I have some morphism F, I can do it first and then do this sort of braiding thing. So F goes from C to D, and I can use the D structure. So this is mu sub D, sorry, S sub D of mu. But I can also do the braiding on the C's first, and then do these F's. So this is F to the third power composed with that thing, and this is S sub C of mu composed with F's. The fact that so the request that F be an S homomorphism is precisely this equality, but you can verify that, again, just by the magic of string diagrams. So you can see that just by the ambient structures in any symmetric monoidal category, it's always going to supply these notions of bijection. But more interesting is when supplying something actually gives you some extra structure. So something you can work with. So there's this notion, it's well known, called a self-dual compact closed category. And that's exactly, it can be redefined as saying that C supplies these duality things D. So C supplies D if and only if C is self-dual compact closed. So if you don't know what this sort of particular structure is, I can at least give you an example. So there's the category of matrices over the real numbers with the tensor product of matrices, of the Kronecker product, tensor product of vector spaces, Kronecker product of matrices as the monoidal product. And so this thing, because it's self-dual compact closed, supplies these dualities And how does it supply this? Well, if we pick an object, so objects of these in here are the form r to the m. If we pick the object r to the m, then there's always a map from the monoidal unit r to r to the m tensor r to the m, which takes some real number lambda and maps it just to this, the diagonal matrix, basically. So you can think of these as matrices, square n by n matrices, with the components being, with the indexes being sort of this factor and this factor. So this thing is the diagonal matrix of lambda, like this. Then we also need a map for the other generator D. So this is a map from r to the m tensor r to the m to r to the n, just to r, sorry, the monoidal unit. And what this does is it takes an arbitrary element here, which we can think of as this matrix with entries lambda ij, and it takes the trace, so it sums over the diagonal. Yep.
Is there some intuition for the right-hand side of the if and only depends on C and not D?
So the D is the notion of self. D is the algebraic theory of self-duality. So C supplies D if C supplies D. Is that?
D is the theory of self-duality. And it was written on the board up there.
Oh, D is not an arbitrary D.
Yeah, sorry.
Okay.
D is this particular thing.
Okay. My bad.
Good question.
So mat D, sorry, the category of matrices, which you may really enjoy working in, supplies these dualities, and this means that in the category of matrices, if you have some matrices, you can, for example, take the trace of the matrix, or the partial trace or something, and these constructions make sense in that category. What's also nice is that this notion of homomorphically supply homomorphism returns the notion of an orthogonal matrix. So for reasons of time, I won't go into too much depth, but one fun fact you might like to know is that if you take F and then you do this construction in the category of matrices, I can draw these diagrams again because I'm working in a world that supplies D, so these things make sense, then this is the same as F transpose. And because of this, what does the notion of supply homomorphism say? Well, it says something like, it says, supply homomorphism says I can do my F's and then do my thing, or I can do my thing and then do my appropriate amount of F's, which is 0 in this case, and these two things are equal. But what this turns out to say is if you sort of use this factor to move this around here and think of it as a transpose, and it says that F transpose is equal to the identity. So this is true if and only if F transpose is equal to the identity. So I think that one's called isometry. So it says that something is a cap homomorphism if and only if it's an isometry. The cup homomorphism is like a co-isometry, I guess. And in particular then, F is a S-hom in this case if F is an orthogonal matrix, where orthogonal can be defined to sort of mean that the transpose is its inverse. So again, we see sort of working in this abstract world of sort of supply. I'm just saying I have some category, I pick an algebraic structure in each object, and then by asking questions like what is homomorphic with respect to this algebraic structure, I extract out very well known and useful things. But now they have this nice graphical characterization, which can be helpful for reasoning about them. Okay. I'll end with a last example that goes back to where we started. Sorry, I want to talk about this prop F, so I'm going to work over here. actually, I want to talk about f op, but hopefully we can cope. So one nice statement is that there's this category of relations between binary relations between sets. This is a monoidal category with the Cartesian product of sets and the one object set. And this supplies so sort of slightly shifting to a new terminology by just naming the algebraic structure. But this supplies commutative comonoids. But what I mean by that is that it supplies f op. So supplying f, I guess I erased that, but that meant supplying commutative monoids, and so supplying f op dualizes it to commutative comonoids. So I'm saying that there's this category of relations, it supplies f op or supplies commutative comonoids. And I can tell you what that is on the generators at least. So this thing on some object A should be a map, a binary relation from A to A times A. I guess I'll call it S of A of delta. Delta being the transpose of mu. And what is this binary relation? Well, it's a subset of A times A times A, and it's going to be the diagonal subset. So this thing is equal to diagonal subset. And I also get, so the other thing I need to tell you just about to tell you a commutative comonoid on this object is to give you a map from A to the terminal set called S sub A of epsilon. And this is just the subset A considered as a subset of A times 1. So so what do I mean by this then? There are a couple of things you can verify. You can verify that these things obey the commutative comonoid laws, and that basically they're just the diagonal example that I led with. So you can take this functional intuition and verify it. You can verify this sort of notion of supply. So what this means is that there's a functor from f up to rel, which is given by this data.
For every object.
For every object, A. Anyway, there's the statement. So I've given you enough data to actually prove this fact. But an interesting thing to note here is that supply homomorphisms with respect to this supply are functions. So we can pull out the notion of function by talking about supply homomorphisms with respect to this algebraic structure inside the category of relations, which is a cute fact to play with. But finally, I want to state a slightly more general theorem, which is that if we take any monoidal category, we could ask it to homomorphically supply these commutative comonoids, so f up. And this is true if and only if homomorphically supplies f up. This is true if and only if this tensor is not only a monoidal product, but is the categorical, or is a categorical product.
And I is 1, or do you need I also to be 1? That terminal?
Oh, yeah, okay. And I is terminal. So another way of stating this using more jargon is that a Cartesian monoidal category, so that's exactly what this is, a monoidal category where the monoidal structure comes from the categorical product, is exactly, so a Cartesian monoidal category is exactly one that homomorphically supplies commutative comonoids. And the basic idea here is that, so categorical products say that for any objects x and y and some other test object A, homs from A into x times y are sort of in natural bijection with pairs of homs, one from A into x and the other from A into y. And so how do we get this correspondence between them? Well, if I have some morphism H going from A to X times Y, I can produce, if I have these, this eta map, H, this pair, where I throw out the second variable to get a morphism from A to X, and I throw out the first variable to get a morphism from A to Y. And then conversely, if I'm given some morphisms F and G, I can produce a morph which go from A to X and A to Y, and I can produce a morphism from A to X times Y by, well, I can tensor product them and I get a morphism from A times A to X times Y, but I have this duplication map. So I can produce a morphism from A to X times Y just using the comonoid structures. And then you have to ask, well, are these morphisms inverse? And that exactly is given by the homomorphic nature. So it's about the verification that these two things are inverses is fairly straightforward, and it's about passing these sort of F's and G's through the co-multiplication, or this diagonal map, and similarly about passing the H through the co-unit map. So that's about time, so I think I'll wrap up there.
Could you say something about what sort of what is the take-home message from all this? That I guess the point I'm getting from it, tell me if I am anywhere near correct, is that you're trying to leverage the power, the visual power of string diagrams to do deep reasoning about things, and you're sort of building the machinery underneath it to justify that this all works, I guess.
Yeah.
Because I guess I have this notion that at some point we could build software that would allow us to do really important and meaningful things graphically.
Right.
And so if you can build the mathematics underneath that, then that would be helpful.
Yeah, I can't say anything better than that. That's exactly.
Damn.
Well, maybe you could say that you're supplying new icons, right? So.
Oh, okay. So I was wondering what the word supply was.
Like you're saying, in any monoidal category, I have string diagrams where I can do things in parallel and series. But now I know I can duplicate stuff, and I know I can throw stuff away, and I can do that to any object I want. And so if you say that, then you're supplying throwaways and you're supplying duplicators. And so P this prop is all the things that you're giving people the right to do in anywhere in their string diagram, and the rules about how those things play together.
Yeah. Sam?
How does this compare to algebraic theories, where it seems similar because you have this like syntax category and functors from that set are these algebraic objects?
So the perspective is very similar. The logical power of what you're giving yourself is slightly different. So one, I mean, from the point of view of what you might use it for, Levere theories tend to be, Levere theories, you start with this sort of finite product category, right? Or you start with sort of this notion of variables somehow. In fact, you use this category F up a lot, which allows you to sort of duplicate stuff and throw stuff out. And so it's sort of resource insensitive. It sort of deals with classical information. Whereas when you move to a more prop-based perspective, you're much more resource sensitive. This sort of tensor product does not have these nice properties that this Cartesian product has. And so your reasoning looks different from that perspective.
You get like a linear logic or something?
I was tempted to say those words, but they're not as, they're not bad words to say.
I'm sure you have.
They're not the best. I don't know whether I fully endorse that.
Wait, so is a homomorphic supply somehow like the mapping from C to a sub C being functorial in some sense, or? So could you have?
Yeah, there's this really pretty way to view all this that I didn't really, somehow was way too optimistic. But there's a better way, or there's another way to repackage this definition, And you take C naught to be just the category generated by the coherence maps in C. So it has all the objects and it has like your associators and your symmetries, but nothing else. It's just very bare bones. And then you take C, and there's a natural inclusion functor from this category into this. But there's a whole category of strong monoidal functors from here to here. And so a supply is what sort of functor? I guess a strong monoidal functor from this theory into this thing such that if you take the natural number n maps to sort of this inclusion functor to the nth tensor power, plus some sort of bookkeeping condition that looks like D, but then I'm going to sweep under the rug. But then what you're saying is sort of, well, what happens is that this definition is equivalent because this definition implies that all the coherence maps are already homomorphisms for the supply. And so more generally, you could replace this with a larger subcategory of C, or just, I don't know, C prime subset C. And then when you use this sort of definition of supply, you're saying, I want C to supply P's such that these morphisms in C prime are the homomorphisms.
So if you took C prime to be C, then you get homomorphisms.
Yeah.
You can like swap the arguments. Not you'll just like this.
Sorry,
Like if you like if you like curry and then swap and then curry.
Oh,
right.
You'll get something that's more like this.
yeah.
Yes. So,
Yeah.
yeah, this perspective still feels very, very abstract to me in some ways, but it works really nicely because then you can say, for example, if you have functors between props, so for example, there's an inclusion of, I don't know, nothing great, but bijections into F. So if you supply Fs, then you also supply bijections. Anyway. How are we on time? Should we?
Let's stop.
Okay, we'll break for now and then we'll go to questions in the common room. Great, thanks.